Okay, so this colloquium, I'd like to introduce our own Nick Harvey. Nick has an interesting blend of theory and practice. After from a software engineer, before he went on to get Best Student Paper Award for 5 years, and then to my research and was successfully lured here with a CRC, and he won a 2013 Sloan Fellowship. So, and I guess he's going to show us some of his theory and practice blend. So,
okay, great. Thank you for the introduction. Work that I did with the group of people listed here, all of whom are jointly affiliated with UBC and, okay, sorry, it's not on? The light appears to be on. Yeah, the light is on. Is there a second? Okay.
All right. So we'll continue without the mic. I'll try to talk as loudly as I can. So all of the are jointly affiliated with UBC with Coho Data. Coho Data is a startup in town co-founded by Andy Warfield, and the work was done in the context of this startup. So part of my role here today, I think, is to introduce myself to the students in the audience, to give many of you a sense of what I do. So let me just give a brief summary of things that I do. So here's my interests in one slide. So I worked for many years on topics in discrete optimization. So that includes things like graph theory, matroids, and so on. I also dabble a bit in the theory underlying machine learning, and I taught a graduate course on this last term. A topic that I've been passionate about for a long time is randomized algorithms, and I'm teaching a graduate class on that next term. So that involves various tools. It's really sort of bread and butter of techniques in algorithm design these days. And I find that often an area with nice applications of algorithms is computer systems and networking, and I've had several projects in that domain, and today's talk is another one of those projects, so algorithms in systems. So, what is the talk about? When my wife asks me what I do, I tell her that I'm working on caching. Right? What is caching? Caching is basically a way of managing data when you have some fast memory and some slow memory. Okay, so how do I explain to my wife what is fast memory, what is slow memory? Well, let's think of your to-do list, right? You have your fast memory version of your to-do list, and then you have your slow memory version, which is your day planner, which you keep in your backpack. And so when you need to get something out of there, it takes a minute or so to find it. But you have much more capacity in your day planner than you do on your hand, right? You have little capacity for writing things on your hand. So that's a high-level view of what caching is. So in the context of computer systems, caching has been studied really since the very early days, right? So even back in the 1960s, right, computer architecture had many of the pieces we see today, right? You had CPUs with registers, which were the fastest sorts of memory, and you had larger capacity RAM, and then on top of that you had disk, your non-volatile storage. And part of your software had to deal with moving data back and forth between these levels of hierarchy. And so looking at the research literature in those early days, right, one of the seminal papers due to Belady talked about many of the basic algorithms still used today for migrating or managing these various levels of caches, right? So the FIFO algorithm rand and min algorithms, still taught today in our undergraduate curriculum. And another seminal paper from that time, just 2 years later, paper of Denning, that introduced the notion of a working set and focused primarily on the LRU caching algorithm, which is still one of the most important caching algorithms in use today. So how do things look nowadays? So in a more modern view of things, right, we have much more levels of hierarchy in our storage systems, right? So we have our CPU still with our registers and with various levels of cache, RAM, maybe some SSDs, or the flash-based disks, conventional spinning disks, and then maybe you have some web caching on top of that and some content delivery network and so on. So various levels of storage at various distance from our compute. And how do we manage these levels of storage? Well, at the CPU level, this is not something I'm too knowledgeable about, but basically things are so fast that we can't really afford to do anything clever, and you just have some basic, maybe 2-level associative map or something simple like that. But back in the memory to disk level of the hierarchy, we still see LRU being used as proposed in the 60s, and even down at the web caching level, we still see LRU in heavy use. And then for the distributed protocols, different algorithms there. So for the purpose of this talk, we're going to focus really on this level of the hierarchy, where LRU is still dominant. But so why is it that even though things have changed so much since the 60s, right? We have a very different memory hierarchy. Why is it that our algorithm for managing things is really essentially the same as it was? So if we look at how things have progressed, our CPUs are at least 1,000 times faster than they were in the 60s. But our disks are not really much better, right? They're certainly higher capacity, but in terms of latency, they're barely 10 times faster than they were in the 60s. So what does that mean? That means that a cache miss is increasingly costly, right? In terms of the amount of compute that you could have done in the time that you were waiting for your cache to be request to be satisfied, right? You're missing much more of your compute because your disks are just as slow, but your CPUs are way faster. So, given that, right, given this increasing cost of a miss, you'd think you might want to do something more clever than 1960s technology algorithms to manage your cache. Right? So that's sort of one of the motivating ideas of this work. Okay, so let's think of ways in which people have tried to design caches, right? So what are sort of the design space people have used in the context of caching? So suppose you're building a storage system today, right? Suppose you're an IT administrator, right? And you're trying to choose some blend of these storage devices, right? What should you do, right? Should you use a bunch of RAM and a bunch of flash disks, or should you use some non-volatile DIMMs and JBOD, right? Your design space is now really big. And so in order to make a sensible decision about how to design your system, you really ought to have some understanding of your workload, right? What are the properties of your workload, and how will that interact with the different characteristics of your storage devices? Okay, so that's another question that motivates this talk, right? Understanding what goes on in your workload. And here's another motivating challenge. So consider modern servers in the data center. Right. So in current servers, they tend to be very heavily virtualized. Right. So we would have many different virtual servers, right? Your web server, and your print server, your database server, and so on, all being hosted on the same physical server. Right. But your physical server has a fixed amount of fast memory. Let's say it's RAM, right, or it's cache. How should you allocate that RAM amongst these amongst these virtual servers, right? What is the, if you have a certain allocation of your RAM amongst these servers, how do you know if it's a good one? What would be the benefit of increasing the RAM allocated to one of the servers? What is the marginal benefit of giving your print server more RAM? So that's not a question that typically that's easy to answer in this setup. Okay, so part of our goal here is to understand workloads, right? So we want to help these administrators who are designing their data centers make better decisions about buying storage, and we also want to help our operating systems that are dealing with virtual servers make better allocation decisions. So those are our goals. But this is not easy, right? So suppose you were to, if you want to understand your workload, what should you do? Perhaps you should capture it. Perhaps you should store a trace of everything that happens, and then you can go back and analyze what happened. But this would be costly, right? Even in a small setup, we're talking gigabytes a day to store a simple trace. And then even if you were able to store all that, then how would you go back and analyze it, right? If you have a 50 gig trace of what all your virtual servers are doing, or what your storage system is doing, then what sort of algorithms can you use to analyze and distill useful information out of that? So that's another challenge. Okay, so let me introduce you to one of the core object we will talk about today. So this is a hit rate curve, and this dates back essentially to these papers in the 60s that I mentioned, right? Belady and Denning essentially had this idea there already. So the question is, if you have a fixed workload and a fixed caching policy, then how will your hit rate depend on the amount of cache that you have? So if your cache size is X, what would your hit rate be at that given size X? Okay, so the reason why you might want to know a hit rate curve is to help you design your caching system, right? Exactly as Belady was proposing in his paper. So if you know that your workload is going to look like this, then how much RAM should you use to process this workload? Okay, so let me ask you, the audience, right? If you were designing a system and you knew that this was your workload, what do you think would be a good size of cache? Okay, and okay, yes.
Doesn't it depend on the application? I mean, it might be worth it to have like half gigabyte of cache, but at the same time, maybe like 0.1 is enough.
Okay, right. So this is a subjective question, absolutely. But I like your suggestion. So let me just roll with it. So why do you let's think about 0.1. Why did you think 0.1 would be a good choice?
Because I mean, the improvement is marginal, but if that will give me a large profit, why not?
Exactly. So this is really the notion of a working set, right? So as defined by Denning, a working set is the minimal amount of cache you need to get good performance on your workload, which is a rather vague definition, but essentially we can think of it as, you're trying to find this knee or this elbow in your hit rate curve where you will get good bang for buck out of your cache, and sort of from this point onwards, there's not much benefit of allocating a bigger cache to this workload. Exactly. So that's the notion of the working set. And this hit rate curve is an actual hit rate curve that came from a trace that was done by Microsoft Cambridge a few years ago. They ran a trace of their deployed servers for a week, and this is one of their servers, their terminal server, I think. And so we see that the hit rate curve has this nice shape, and we can identify this good working set. Okay, so one of the points of this talk is that hit rate curves don't always look like this. So here is another hit rate curve from exactly the same collection of traces. This is of their web server. Okay, so what is the working set now? Where is the knee in this curve? Okay, so the issue is that hit rate curves do not have to be nice functions, right? They do not need to be concave, they do not need to be smooth or differentiable, right? They're typically monotone, but they can be a pretty complicated curve. And so this notion of a working set really does not exist when you have these complicated hit rate curves, right? There's no, whereas we thought before about the marginal benefit of allocating more cache to one of our servers, right? We cannot really define marginal benefit with this curve, right? Marginal benefit is essentially talking about derivatives, and this is not a differentiable function. Okay, so instead of talking about working sets, let's talk about hit rate curves. Right? That's really one of the messages of this work. Okay. And so, but in order to talk about hit rate curves, right, remember that was for a fixed, they're defined for a fixed workload and a fixed caching protocol. So let's specify our caching protocol. We're going to be talking today just about the LRU caching protocol because it has nice properties and it's heavily used in practice. Okay, so what is the LRU caching protocol? Here's how we could define it. An LRU of cache size x always contains the x most recently requested distinct symbols. Right, so if you look backwards amongst the requests, find the x most recently requested distinct symbols, that's what's going to be in your cache. Okay, and so it seems a bit odd that we're saying most recently used, whereas the name of it, LRU, stands for least recently used. That's because least recently used is talking about what you're throwing away, and most recently used is talking about what you're keeping. Okay, so let's look at an example here. Suppose this is our trace. We're requested blocks A, B, C, A, D, A, B. And now at the time that B is being requested, let's look at the number of distinct symbols that were requested since the last request for B. So in this case, we see that CADA was requested, and there are 3 distinct symbols. Right? A appears twice, so there are only 3 distinct symbols. And this is what we call the reuse distance of B. Right? So when B has been requested, the reuse distance is 3. And going to the definition of LRU, we know that if the cache size is strictly bigger than 3, then B will still be in the cache at the time that the second B is requested. Because if we have 4 units of cache, then it will contain A and D and C and this B. B will still be there. So as long as the cache size is strictly bigger than 3, then the second request for B will be a hit. Okay, so that's hopefully gets you up to speed on how LRU works. And a property that we can notice from this is that larger caches always include the contents of smaller caches. Right? So that implies that the hit rate curve for LRU will always be monotone, as I said earlier. Right? Having a bigger cache, the bigger cache contains the smaller cache, so it's always a hit at the bigger cache size, if it is at the smaller cache size. Okay, so that's LRU. Now let's talk about how to compute the hit rate curve for the LRU caching protocol. So this is an algorithm that dates back to 1970, and it was proposed in a paper of Matson et al. And so here's how it works. So from this inclusive property, we know that a bigger cache can simulate a smaller cache. Right? A bigger cache has all the information that a smaller cache has. So we can use a bigger cache to simulate the smaller cache. So why not just take the biggest cache possible, right? N. Let's let N be the number of distinct blocks. And we will simulate a cache of size N, which also allows us to simulate all smaller caches. So what we will do is we will keep a list of all blocks sorted by their most recent request time. So let's see how we do this in this example. So first A is requested, and so we put that in our list. Next, B is requested. We move B to the front of the list because it's now the most recently requested block, and A shifts forwards. Then C is requested, so C is now at the front. And then A is requested again. So instead of inserting A at the front, we will move this old A now to the front of the list. So now A appears at the front, and C and B shift forwards. Okay, and at this point, we can determine that this second request to A was a hit, right? Because A was already in the list, and its distance, its position in the list, indicates so that's the same as the reuse distance that I mentioned earlier. Right? Its position in the list is equal to the number of distinct blocks that were requested since the previous request for that block. Okay, so if that, and then we can record this in our hit rate curve. Right? We know that when we see that the position is D, then this is a hit for all capitals at least D. So then we add that to our hit rate curve. Okay, so if we keep processing, now D goes to the front, then A is requested again, so A will move to the front, and then B moves to the front, and so on. Okay, so that's Matson's algorithm. So one question one might have, as thinking algorithmically, is how much time does it take to run this algorithm? Right? Is this going to be efficient? Well, if you have, and if these traces really are tens of gigabytes big, then one really ought to be concerned about the runtime of this algorithm, and not only the runtime, the space usage as well. So it turns out that there's been a lot of research on that, right? Coming up with faster versions of the Matson algorithm. So here's essentially the state of the art there. So we will maintain a table mapping each block to its the time of its last request. Right? So here, so if we're processing the second B, A was last used here, D was last used here, C was last used here, and so on. So we can maintain a table like that. And now, when we process a request, we want to know the number of distinct blocks seen since the last request for that block. So let's consider the B. We know its last request is here, and we want to count the number of distinct blocks here. Well, that's the same as the number of blocks whose last request time is at least t. Right? If this is t here, then I have 3 blocks whose last request time is strictly bigger than t, or 4 blocks whose request time is at least t, and that's the same as the reuse distance. Okay, so the reuse distance can be computed by looking at these last reuse times. Okay, and so how can we compute that? So it turns out that if we use a balanced binary tree, then this is an order statistic query, or a rank query in the balanced binary tree. So if we use an augmented binary tree, then we can do all these computations in log n time. So that gives so if your trace length is m, then you can compute this whole hit rate curve in order n times log n time, which seems great, right? We now have a nearly linear time algorithm to compute this hit rate curve. Okay, so should we be satisfied with this? Are we done at this point? So initially I thought we were done, but here's the issue. The issue is that the space required by all these data structures is linear in n, the number of distinct blocks. Right, and that turns out to be a huge issue with these giant traces. Okay, so consider a modern disk. Modern disk is, you can buy disks that are 8 terabytes. And our operating system typically divides them into 4 kilobyte blocks. Okay, so the number of blocks on your disk is 2 billion. That's getting pretty big. And in a data center, you might have a multi-disk array. Here's a 60 terabyte JBOD, which again you can just buy online. And here you would have 15 billion blocks. Okay, so imagine trying to run this Matson algorithm using your balanced binary tree with 15 billion nodes in it. Okay, that's going to start to be expensive. And remember, our whole goal with this is to improve our memory usage. Right? And if you're improving your memory usage consumes 15 gigabytes of RAM, right, then that seems like a very counterproductive thing to do. Okay, so the takeaway from this is that in the context of these big storage systems, linear space is really not okay. Right? We need to do better than that. Okay, so just to give you a taste of what we managed to do, so we ran an optimized C implementation of the Matson algorithm on these MSR traces, which is which contained 13 different servers for this 1 week period. The trace file is 20 gigs in size. It contains 2.3 billion requests for 750 million distinct disk blocks, which is 3 terabytes of data. Okay, so this optimized Matson's algorithm took an hour to process this trace, which is not bad, but it required 92 gigabytes of RAM to do so. Okay, so that's the bottleneck that we're running into. That's what we need to improve on. Okay. So what we would like to do, right, sort of stating this in the terminology of algorithm researchers, right, we would like to estimate the hit rate curve in sublinear space. Right, that's our goal. And fortunately, there is an entire literature in the algorithms community on sublinear algorithms that have been studied for the past 15, 20 years. Right, so that's the area from which we will be borrowing ideas to attack this systems problem. Okay, so let's lower our goals to start off with, and instead of computing a hit rate curve in sublinear space, let's see first how to compute a hit rate curve in quadratic space. Right, previously we had linear space, now we're aiming for quadratic space, right? So things are even worse. But sometimes that's a useful approach in algorithm design. Okay, so here's what we will do. We will maintain for every time the set of all items seen after that point in time. Okay, so at the start of the trace, we create a new set and we insert A into it. So this set here is all the items seen since the first request. Then at time 2, so here we have another set. This set contains only B, right? B is everything seen since time 2, and AB is everything seen since time 1. Okay, now we keep going. We see C, and we insert C in all previous sets. And we see A. Okay, now what happens when we see the A? Well, if we look back, we can infer the reuse distance of A. Right? If we look back in time, we see that B and C were requested since A. And so that gives us a reuse distance of 2. And that is the same as the size of this set here. B and so this is one of the sets that we built up, and the size of that set is equal to the reuse distance of A. More generally, the reuse distance of A is equal to the size of the oldest set that grew when we saw A. Right? So this first set had already seen A. It did not grow. This next set here with the B and the C in it did grow when we saw the A. And it is the oldest set that grew. And the size of that is the reuse distance of A. Okay. So we can use these sets to infer all the reuse distances. Once we know the reuse distances, then we can infer the hit rate curve. Okay, so let's keep going. When we see the D, we insert D into all the previous sets. When we see the A, again, it has been seen before, so its reuse distance is 1. That's the size of this set here, the oldest set that had not seen the A. And then when we see B, its reuse distance is 3, not 4, right? So there are 4 symbols here, but the size of this set is only 3. Okay. So we're maintaining this enormous collection of sets, each one of which can have linear size. We have a linear number of sets, each of which has a linear size. So that's a quadratic space algorithm for computing the hit rate curve. Okay, so let's see. Okay, actually, let's not do that. Let's see the pseudocode. Okay, so here's some pseudocode describing the process that I just described. So we loop over the entire trace, or a sequence of requests. We receive a request. We find the minimum value j, such that this new request is not in the jth set. We compute the cardinality of that jth set, and then we record a hit at reuse distance vj. And so here, when we're processing this b, We look back at the oldest set that does not contain B. The size of that set is Vj, and we record the hit at reduced distance Vj. Okay, so that's the algorithm. Are there any questions about that? Make sense? Okay, so let's now see the same algorithm in slightly more abstract terms. Okay, so as before, Vj will be the cardinality of the jth set. And so here's what we will do now. We will define a new quantity, delta j, to be the change in the jth set's cardinality when we insert bt. So remember, previously we were looking for the oldest set that grew, right? And delta is the change in the size of the set, right? So looking at delta allows us to figure out which set grew. Okay, but instead of trying to find that set that grew, here's what we will do. We will look at the change in the deltas. Right, so delta itself is the change in the size of the set, and we will look at the change in the delta, some sort of second derivative of the set sizes. So what does that allow us to do? So if we look at these deltas, so when we're processing this request, these guys had seen B before, so their change is 0. These guys had not seen B before, so their change is 1, right? They grew by 1. And now if you subtract these deltas, what do we get? Well, the differences here, right? This guy here is the difference of those two. They're both 0, so his difference is 0. And these newest guys, these guys are also 0 because, well, these are all 1s. So in delta j minus 1, there is only going to be a single 1, right? That single 1 is this transition point from seeing 0s to seeing 1s. Right? So delta j minus 1 only takes the value 1 at a single place. And that single place is the place, it's the oldest place where B had not been seen. Right? It's the oldest set that grew. So if we just loop over all those previous times, and we record this many hits at the corresponding reuse distance, then we will actually only be changing it at a single place. We're only recording a single hit. Okay, so here's the abstract version of this algorithm that you agreed you understood on the previous slide. Okay. So here's now the question that I would like to ask. So we have these sets, right? Each set here, each column here, potentially takes linear space. So let's think, how would you, if you were to implement this algorithm, how would you represent these sets? What's the typical way to represent a set as a data structure? I just finished teaching 221 in the summertime, right? So this is exactly the sort of question that I would hope my 221 students can answer. All right, so who wants to be bold and answer this 221 question? Let me ask Will, since I think...
Well, I would just use a bit factor.
Okay. Right. Okay. So this is good. Much like in 221, questions do not have a unique answer. Right? All answers are debatable. So bit vector, also a good suggestion. Any other suggestions?
So does it store a variety of subsets?
Yes, we want to store a variety of subsets of the blocks that may occur in the trace. So what's the, I mean, there's many different answers. So what might be a good answer here?
Hash table.
Hash table, great, okay. It flashed up earlier, but yes, this seems like a good answer. Bit vector also a good answer, depending on how much you know about the block identifiers. So that indeed would take linear space. Okay, so let's think about how you might shave off some constant factors, right? So there are data structures that often appear in systems contexts where you want to represent a set, and you might want to shave some constant factors off the size of your hash table or your bit vector. Okay. Does anything come to mind? I'll give you a hint. Randomization is going to start playing a role. so let me move on to the next slide. So we're going to look at, so we're now going to allow ourselves to look at randomized data structures. And here's various operations you might want to support on your set. Right, so maybe you want to support insertion, deletion, membership, and cardinality queries. Okay, so a hash table can do all that. Right, but we want to do better than a hash table, and perhaps because we don't need all those operations. So another data structure that's sort of like a hash table and is randomized is a Bloom filter. So a Bloom filter is a compressed form of a bit vector. And it does not support deletion, but it does support membership queries if you allow some error, right? So that allowing error is what allows you to shave off some constant factors in the size of the data structure. Okay, so the Bloom filter could be good, but we were not exactly using membership queries. And shaving off a constant factor may not be good enough for our purposes. So what else can we do? It turns out there's another randomized data structure that is exactly what we need. And that is called an F0 estimator. Okay. And it also goes under several other names, such as a probabilistic counter or a distinct element estimator, and also commonly known as hyperlog. Okay, so what does an F0 estimator support? It supports insertion and it supports cardinality queries. It does not support membership queries or deletion. Okay, and that is key because there's an easy lower bound saying that any data structure that supports membership queries must use linear space. And but fortunately, we don't need membership queries, and so that will actually allow us to go to sublinear space. So that's one of the key ideas. But actually, we will first only go to subquadratic space, right? Because we were previously at quadratic space, and now we're going to go down to subquadratic space. So basically what we will do when processing the sequence of requests is instead of storing that set for every time step, we will instead store an F0 estimator for every time step. So we will, when we process A, we create an F0 estimator, we insert A. When we process B, we insert it into both of the previous F0 estimators. Insert C, we create a new F0 estimator, and so on. Okay, now remember what we said, the reuse distance is the size of the oldest set that grows, right? And that comes from a cardinality query, right? We're using cardinality queries to measure the size of the set, and we can detect the change in the size of the set by those cardinality queries, right? So the previous pseudocode that we had that was just using those cardinality queries will still work with this F0 estimator instead of the set. Okay, now there will be this issue of error that needs to be addressed, but we'll get to that later on. Okay, so essentially, the pseudocode is essentially unchanged. We just let Vj now be the value of the F0 estimator. Delta is the change in the F0 estimator, and we update, or we record the hits as before. Okay, so we're still only at subquadratic space. What we would really like is sublinear space, right? So how can we do that? So the first observation is that these F0 estimators, or these sets, have a special property. Right? The special property is that the older sets are always supersets of the younger sets. Right? So looking back, we can see that here. Right? The oldest set is always the biggest, and the youngest set is always the smallest. And more generally, you have that containment property. The older sets contain the younger sets. And so that seems like a useful property that you might be able to leverage to work towards sublinear space. But in order to talk about that, I need to tell you how these F0 estimators work. Okay, so what is an F0 estimator? So these date back 30 years. So they support this insertion operation, and they support this cardinality queries, but they allow a certain amount of error. And And precisely, they will guarantee that the value that they report is within a 1 plus epsilon factor of the true value of the size of the set. So you have 1 plus epsilon multiplicative error. And so let's describe a version of this that uses only log n over epsilon squared bits of space. And it turns out that the optimal algorithm here is known due to K, Nelson, and Woodruff. They show that actually log n plus epsilon, 1 over epsilon squared is the optimal number of bits to use to solve this problem. Okay, but let's not worry about the optimal result. Let's just aim for this result. So here's basically how it works. We create a table of bits. The table has log n rows and 1 over epsilon squared columns. And here's how we do insertion operations into this table. So when we see an A, so we will have 2 hash functions. Right? The first hash function we will use to choose a column. And that hash function is simply a uniformly distributed hash function on the columns. So first we pick a column for A. Then we need to pick a row. The row function is a little bit different. So it will not be uniform. It will be a geometrically distributed random variable, meaning that with probability half, you go to the first row, probability quarter, you go to the second row, probability an eighth, you go to the third row, and so on. So you have these exponentially decreasing probabilities of going lower and lower down in the table. Okay, so you apply those 2 hash functions. That tells you the key entry to update. And in fact, you'll update all entries above it as well. Right? So you set that entry to be 1 and all entries above it. Now B, we hash it again. It goes here. We set that to a 1. C goes here. We set that to a 1. A appears again, and nothing changes. Because these 2 functions are hash functions, they point you to the same place, and so you will make the same updates the second time that you did the first time, so nothing changes. And maybe the D goes here, and it updates 3 entries, and so on. Okay, so that's the insertion procedure. What about the cardinality queries? So if you had a table like this, how might you estimate the cardinality of the set that you saw? So basically, the idea is that if you look at a single column, right, you have the depth of the deepest one you see in that column tells you something about how many items appeared in that column. Right? The more items that hash to that column, the more likely it is that some of them will end up very, very low in that column. And maybe combining those estimates from multiple columns will give you a good estimate of the cardinality. So that's exactly how it works. So suppose you insert n items into this table, then roughly n times epsilon squared of them will go to each column. And so the number of ones that appear in that column is the maximum of this roughly n times epsilon squared geometric random variables. Right? And looking on Wikipedia, you can learn everything you possibly wanted to know about geometric random variables. And you can determine that the max will be approximately log n times epsilon squared. So you'll have this decent estimate for the value log n times epsilon squared by looking at the deepest one in any column. Okay, and now if you average that quantity across all the columns, you will get a really, really good estimate for that value. Right? So by averaging, we get this excellent estimate for log n epsilon squared. And now we can just exponentiate that and scale it down, and that will give us an estimate for n. Okay, so that's a sketchy description of how F0 estimation works. And the magical thing is that it only takes this table, which has log n over epsilon squared bits. Okay. But we were in this special scenario where we had many, many estimators, and they formed this chain, right? They had this containment property where the older sets contained the younger sets. So now let's try to modify the F0 estimator to support that scenario. So basically, it's very simple. So instead of having this bit vector, or this table of bits that we had before, we will turn it into a table of words. Okay. And then when we update the table, instead of putting ones into the table, we will simply put the time at which this operation is happening. So when A hashes into the table, we fill it up with 1s, as we did before. When B hashes into the table, instead of putting a 1 there, we put a 2, because this happened at time step 2. When C goes in, we put a 3. And now when A appears again, previously we didn't update the table, it already had the 1s. But now A is appearing for the second time, and we update the time step. Right, so we put now 4s in this location where A appears. Okay, and then it continues as before. Okay, so why do these timestamps help us out? Right, what is the useful property that they allow us to do? Okay, so now when doing a cardinality query, right, the cardinality query, we're trying to determine the number of distinct elements seen since time t. Okay, but we've timestamped all our changes to the table. So if we just look at all the entries of the table that have timestamp at least t, then that pattern is exactly the same as the F0 estimator would have been if we started it at time t. Right, so we can extract from this table of words all of the bit vector or bit tables that we would want for any point in time. Okay, so that's it. So for any time t, we can estimate the number of distinct elements since that appeared since time t, just using the regular F0 estimation process. Okay, and so what is the total space required? We still have log n rows, 1 over epsilon squared columns, and then we have a word in each entry of the table. So log n over epsilon squared words is all we need to do cardinality estimation for this chain of subsets. Okay, so now let me state for you the theorem that says how well this will do. Okay, so using that same HRC estimation pseudocode we had before, together with this F0 estimation on a chain, we get the following result. So if C is the true hit rate curve, and C hat is our estimated hit rate curve by this process, then our total space required ends up being this. So order B squared, okay, so I didn't tell you yet what B is. So as before, n will be the number of distinct blocks that were requested. M is the total number of requests. And we will, essentially we want to divide things up into to bins. So we will assume that n is equal to b times w. So let's just assume that n is a multiple of w. B will be the number of sort of our accuracy of the hit rate curve, and w is sort of the width of each bin that we get by this binning procedure. Okay, and then the amount of space we use is this quantity. So order b squared times log m over epsilon squared words of space. Okay, that's a bit of a mouthful. The key point is that it essentially does not depend on n and m. Right? It only depends logarithmically on n, the number of blocks, and m, the length of the trace. It only depends polynomially on b and epsilon, and those control the quality of your plot. Right? B is the number of bins in your estimated hit rate curve. Epsilon is the amount of error that you're willing to tolerate. Right? So it depends polynomially on those error parameters and logarithmically on the actual size of the request sequence. Okay, and here is the guarantee that we get on the accuracy of the estimated hit rate curve. That is kind of a mouthful as well, but let's try to figure it out. So basically it's saying if you look at the jth point, or the jth bin, then it is up to this epsilon error pretty close to the j minus first bin in the true trace and the jth bin in the true trace. Okay, that still may be hard to digest, so let's break it into pieces. Basically, we are allowing two types of error. We have this horizontal error, because we are only comparing the jth bin in the estimated curve to the j minus first bin in the true curve. And then we have this vertical error of epsilon that we allow there. So let's draw a picture of what this is. Okay. So here is, let's let the green line be the hit rate curve, and let's let the blue line be the estimated hit rate curve. then this is a plot between 0 and 1. And it really has, involves B bins. And the width of each bin is W. Right, so we're only sort of guaranteeing accuracy on the granularity of these bins. And what we're guaranteeing is this, this up to this horizontal and vertical error. So let's sort of see an example of what's going on here. So here's the true hit rate curve in the jth bin. Here's the true hit rate curve in the j minus first bin. And here's our estimate. Notice the estimate looks pretty far off here. And the reason it looks far off is because it is being compared to the j minus first bin minus epsilon. So if we take this j minus first bin value and we subtract epsilon, we are way down here. We are guaranteeing that it is at least that. Right? This estimate here is at least this guy minus epsilon. All right, that's the guarantee that we can give. It seems a little bit convoluted, but that's what we can do. All right. So that's so that's a theorem, right? That's an ironclad guarantee. Right? There will be for any trace, no questions asked, you will be guaranteed this accuracy. All right. So how does it perform in practice? So let's go back to these Microsoft Cambridge traces that we discussed before. I told you that it took 92 gigabytes of RAM to process this with the optimized Matson's algorithm. Here's what we can do. We can process it basically 4 times as fast and improve the memory usage by at least a factor of 1,000. And in fact, our implementation is in Java, and most of that 80 megabytes of RAM is the garbage collector. Right? So if this were implemented in C, I would expect something on the order of 1 or 2 megabytes of RAM. Okay. And what about the accuracy? So here is this combined trace of these Microsoft Cambridge traces. So there's 3 graphs being plotted here. The blue one is the true Matson's algorithm. The red one is our algorithm. And the dotted one is some heuristic that's popularly used. So we see that on this combined trace, our algorithm has essentially no perceptible error. Right? And the heuristic also did pretty well on this trace. But the heuristic still used linear amounts of RAM. Right? So it's only our algorithm that has sublinear memory usage. Okay, here's another trace from the same collection. So this is a trace of a source code repository. And again, we see that our algorithm has essentially no perceptible error. The heuristic is starting to see some artifacts here at the inflection points of the curve. And now back to this highly non-differentiable curve that I showed you before. Even for this very complicated curve, our algorithm is still essentially perfect. And the heuristic now has some major artifacts that are visible. Right? And the reason is that basically this heuristic is assuming some sort of statistical properties of the request sequence. Right? It's assuming that you're sort of in this stationary distribution, and as long as you stay in that stationary distribution, then everything will work well. But in this web server, that assumption is not satisfied. Right? This is it turns out it's both a web server and a SQL server. Right? So it has sort of multiple access patterns going on the same server, and the heuristic cannot handle that intricacy. Okay, so let me now wrap up. So to conclude, the point of this work was workload analysis by measuring uniqueness of the trace over time, uniqueness of the request sequence over time. Right? And it turns out that reveals a lot of properties of your workloads, such as the hit rate curve, which tells you a lot about how the cacheability properties of your workload. Okay. And a takeaway is that the whole notion of a working set, which assume these nicely differentiable concave or convex hit rate curves, is not satisfied by realistic workloads. And what we've showed is that hit rate curves can actually be computed in a very lightweight manner. Right? So prior to our work, hit rate curves were these very heavy-duty objects, right, that required massive amounts of RAM to actually compute. We've shown that hit rate curves can be computed very cheaply. And so in systems, there's anywhere where you might want to use a working set to understand your processes or your workloads, you might as well just use the whole hit rate curve instead, because you can now compute them very cheaply. And we can compute them in sublinear space and very accurately as well. And compared to the heuristics that were in the literature and still use large amounts of space, our accuracy is significantly better. Okay, so let me wrap up with some open questions, right? Since this talk is targeted at graduate students, these are some questions that you may be interested in pursuing in your graduate studies. So one question is about the optimality of our algorithm. So the space, the usage that I reported earlier in the theorem was order b squared log n over epsilon squared. Okay, so how many of those terms are necessary? I know the epsilon squared is necessary. The other ones I do not know to be necessary. So potentially the b squared could be shaved down to just a b. That would be quite interesting, right? That would save another factor of 100 or so from the space of the algorithm. We did not talk about runtime, right? I sort of swept that under the rug. The runtime would also depend polynomially on b and epsilon. I don't know that to be necessary. Maybe each request can be processed in constant time, or maybe there's a small dependence on b and epsilon. Okay, and our whole method was based on essentially taking differences of these F0 estimators. Right? We were looking at the growth of these F0 estimators as we update them. And that seems rather crude, right? So we were doing that by subtracting the values of these F0 estimators. And there may be something more clever that you could do. Right? If you have that whole table of, remember the table with log n rows and 1 over epsilon squared columns, right? If you have that whole table available to you, maybe you can get better estimates of these differences better than just doing these subtraction operations. Okay, and here's a more open-ended question. So if we think about these streaming or sublinear algorithms, these originally came up were heavily used in the networking and database communities. But there has not been much use in the storage domain. And one of the takeaways from this work is that even if you have a single computer, right, and you would like to understand some properties of the local disk, right, even that is not necessarily a cheap operation. Right? You can't afford to go looking through the metadata of your file system on your local disk just by accessing it directly from the disk. Right? You would really want to do some processing of that metadata in RAM, but very cheaply using sublinear space. Right? So there may be many more applications or uses of these techniques in the systems domain, and that seems like a nice area to study. Okay, thank you very much for attending the talk.
We have time for questions.
Will?
So, B surprised me, like this capital B. It came out of nowhere. And it seems like it's a sampling thing. Like you're subsampling this curve at several spots. And you're claiming that for a length n curve it's constant, or length n curve is constant. So how do you know you're only getting your accuracy guarantee every 100 spots along this curve?
Essentially, yes. Okay, so the question is about why did the B show up? So there's a couple of reasons there. So one is that the pseudocode that I presented not only used quadratic space, but also quadratic time. Because at every time step, you were looking at all previous time steps and doing the insertions there, and computing the changes in the set sizes and so on. So one reason is to sort of tone that down. If you know that you only want your plot to be accurate up to, say, resolution B or with B bins, then there's no need to examine all previous time steps. You can sort of do some subsampling of those. So that's one explanation. But potentially the B is not necessary. So I don't know the B to actually be necessary.
Is there a question? Yeah, I'm
A question about the F0 estimator. You said that it does give you cardinality, it doesn't give you membership trees. So couldn't you implement membership by insertion and then checking for dead?
Okay, right, okay, that's a good question. And similarly for the Bloom filter as well, can you implement cardinality queries by using its membership queries? So the answer is sort of, it depends.
It would be probabilistic still.
It's not so much it's more the accuracy guarantees that are an issue. So if you have a set of size 1,000,000, then when you insert that the millionth and first, the next element, the estimate will not change. And insert this one again, it will not change. And it will take quite a long time for the estimate to even change at all. So say epsilon is 0.01 or epsilon is 1%, then you need to insert, say, 10,000 items before the cardinality estimate will even change at all. And so you're not really getting any useful membership queries out of this. Right? You're saying, okay, if I inserted 10,000 items, I know that at least one of them was new, was not in the set. But it's maybe not the guarantee you're looking for.
Another question that I had was, it seems like you've kind of transformed membership, I guess, transformed the problem of membership into cardinality.
Yes.
The difference of cardinality. And I was wondering if that's like it just seems a little maybe inefficient, or it seems like you've taken a jump. Like why transform it into cardinality?
Okay, so the reason is because if you wanted a data structure that supported membership, you're doomed to linear space. And if you want to get sublinear space, you need to go into the realm of cardinality instead of membership. So that's exactly why we do it.
So does that mean that the membership that you're getting out for the solution to the problem is going to be necessarily an estimate?
Yes, it's definitely an estimate. Yeah. But going to this realm of cardinality sort of allows you to do this sort of very low space estimation that ends up being useful for this problem originally phrased in terms of membership queries. Michael?
Okay, just wondering if there's more structure in the problem that you can take advantage of in terms of the least recently used set over at least over small intervals, over small distances. It will often be just very similar, and just because of the structure of code, and that therefore, if you could model that in a more compact way, then you get rid of. So the algorithm seems like it's structured for the worst case adversary, or at least the error bounds, whereas in reality there is a lot more structure to the traces, presumably.
I see. Yeah, that's an interesting question. So, indeed, theorists are very prone to think in terms of worst case analysis. So that is the viewpoint here. So interestingly, there were people, so the heuristics that were out there indeed were designed to work well for the scenarios that you described, where if you assume some statistical properties of your request sequence, then the hope is that these heuristics would do well. And they do pretty well, but even they have significant space issues. So somehow it's interesting that in this case, even though we're doing worst case analysis, we still get drastically better space than the heuristics. It's not clear to me. Yeah, I mean the space usage really just comes down to the F0 estimator, and even there, yeah, I mean, it's not clear how statistical assumptions could help there, but potentially they could.
So I'm not sure if it's the same question that was just asked, but if your hit rate curve is well behaved, I mean, is there some, and you somehow suspect that that's the case, is there some way of exploiting that it is in fact smooth, or that would actually give you the opportunity for getting a good estimate with less space, or use the same space in less time, or?
It's an interesting question. I don't see what to do there, but maybe it's related to Will's question. Right? So Will's question was, why did B show up? Is the B necessary? Maybe these questions that you and Michael are asking are tied into that. Maybe in those easier scenarios, it's easier to get rid of the B.
Okay, if there's no more questions, many thanks, Nick.
I'm very sorry. I mean,
Oh, you're sitting here. Subject. I think.
Oh, no.
I know, but it felt hard.
That was our side. So do you need an estimator for every item that you're going to operate? Right? So that's your estimate for everything you can stop. This is nice.
Your interest, but it also somehow ties in nicely.
Yeah, I guess they're correct.
Of course,
Number of zeros.
It seems like it's LRU communication you eventually will.
Right. So So initially, it doesn't matter, right? So with this F0 estimator using the table of words, yeah, it's even if you store it for everything, you have a trace of length. I know. The only depends on n is still a logarithm. It's just in the size of the word. Yes.
Okay.
Yes.
And that's just somebody that doesn't live
Exactly. Exactly. So if you're using
Thunderbird parking.
Anyway, you were saying where
as long as you handle less than 2 to the 64 requests.
But all the easy stuff in terms of
That's a very nice and clever idea. Nick. Thank you.
from the business presentation.
okay,
This is piece theoretical machine learning keywords. Like, I missed it. And I really want that machine learning in that context. Theoretical.
Oh, it is, yeah, it's a fine art for doing the right filming for this kind of stuff. Presumably one gets better with practice, but yeah.
No, so next time we're teaching randomness algorithms.
Okay.
It'll be a bit different, but
Is it?
not different enough for you, I think. We'll talk about some of these streaming algorithms.
Okay. You talked a little bit about
Yes.
that. Actually. Only
One
that.
lecture.
Yeah, in databases.
L2 estimation.
Yes, we did L2 estimation.
Yeah, so you can see how much you know about the topic. We can't even agree on the topic.
By default.
It's like many
Some of
things.
maybe 5 or 6.
Active learning.
Oh, wow. That's surprising.
Much more on the local level. So,
Really?
which I know is your favorite.
Yes, yeah, I just don't remember, yeah. It was my favorite. Not machine learning. I really hope they should actually open, like 2 days ago I was looking at their website.
I think, you know,
Oh, yeah, sure, yes.
your I think it would be.
It seems like everybody else wants to teach that kind of material, like in that rigorous setting. Yeah, so.
You should share your opinions with people other than me. For example, Michael.
I'm hoping like, the course about theoretical machine learning and stuff with the game.
Oh, yeah.
Yeah, I missed that one.
Yes.
I mean, I agree there ought to be a course on that.
Yes.
I could conceivably teach it again. What would be even better is if we
The one that
hired someone who did that as their full-time job.
Oh.
Someone who works full-time
Have you
in
seen the lab? It's really
the
big.
theory of machine learning.
And then just
Yes.
was generally
Well, how was the course anyway? When you taught it, was fruitful
the vision.
as much
the
as
one that Bobak was in.
randomized algorithms as usual. Randomized
Part
algorithms.
of the same.
And because basically it is
Machine learning
area
and
of expertise, right?
Right.
Yeah, so how did that?
It's like us.
Radical machine.
I mean, the students on the whole enjoy it.
Okay, yeah. Yeah, I mean, I'm saying that because I enjoyed randomized algorithms. I did some more advanced analysis course like that, no? So it would be nice to see the application, especially with functional methods, like, yeah, so the Hilbert space here.
how do you find it? It's like,
So I'd like to see that, and I thought it's time, you know?
Yeah, it's conceivable I could teach it again, but it depends on many things.
I'll be here for a couple more years at least, so. Yeah, here's a chance. Well, thank you, it's a nice talk. Okay, thank you.
Yeah, no, great. Thanks for talking. Super stuff. Yeah, very cool.
Oh, no.
So when you talk to Andy, how much do you care about the two extremes of the hit rate curve? Because presumably you have some kind of idea of which part of the hit rate curve you're kind of most interested in.
Okay, so
Because your algorithms kind of makes it sweeps the whole hit rate curve, and the error metrics are kind of the same everywhere across the curve. I think.
Okay.
But presumably you care a lot about, there's a sweet spot that you care about, right?
okay, so here's the issue. The issue is virtualizations.
Oh,
So that's exactly the scenario.
Right.
So you have, task A, its hit rate curve looks like this. You have task B.
I was going to ask you about this, yeah, because these must interact somehow, right?
Exactly.
In some crazy multi-dimensional setting.
Exactly.
Oh, okay,
Yes.
so it
What's
does make
the,
sense.
what's the ultimate allocation for these guys?
Cool.
Who knows?
Yeah.
So